Okay folks, hello, welcome back. So it's another data analysis video, and this is the third and final video I'm going to do on chi-squared. So in the first two videos, I demonstrate how to conduct a chi-square goodness of fit test, how to calculate that manually, and also using the scipy software library. And in the second video, I demonstrate a similar sort of thing, but this time using the chi-square test of independence, where we've got two categorical variables. So we'll look to see if they are independent or associated. And in both of those videos, both those cases, I used data that was made up and been simulated by myself to demonstrate the different steps. So what I'm going to do in this video is kind of run a test of independence on a real data set. So I'm going to import some data and it'll turn out we get a significant association between the categories we look at for this data set. And then what I'll do is I'll talk about kind of follow-up things you would need to do in terms of like post hoc tests thing to say where these significant associations lie. What is it that's driving the significant association? Which levels differ or associated in some way. And what I'm going to do when kind of the data I'm going to import is it's a data set. I believe it comes from the Tabashnik and Fidel multivariate statistics textbook. So it's one that I use on my postgrad courses, and it comes with a number of different data sets. And the one I'm going to import here and use here, it comes from there. So it's kind of health data from a very large sample, measures a number of different things. And we're going to use a couple of categorical variables to conduct a chi-squared test of independence. There are a number of data wrangling steps that I will need to do once I've imported it, and I've left those in. I could have kind of tidied it up beforehand and skipped these, but I've left them in to demonstrate really how in most cases you have to really care about what your data looks like. In most cases you don't get it in a nice neat format that allows you to just run the analysis. So things you have to do to manipulate, wrangle the data to get it into the sort of order that you need it in to be able to effectively perform some sort of analysis. So I'm going to import the data. I'm going to save it as an object called health, and I'm going to use the pandas pd.read_csv method, and the data frame is it's saved as a CSV file on my laptop. It's called health.csv. So I'm just going to pass that as a string, and we'll call the head of this data frame. So it's a number of different variables measured: time at the doctors, number of visits to the doctors, physical health, a measure of that, mental health, a measure of that, stress, some score on stress, religion, which is shown as integer numbers 1, 2, 3, 4, and race, which is categorized as either one, white or non-white, essentially one or two, essentially is what's recorded as. So if religion and race are the two categorical variables we do this analysis on, but they're currently, if we look at data types, everything's been imported as an integer because it is features as an integer numeric value in the data frame. So the problem with this, let's look at the info as well. I'll run that sort as well. So yeah, it'll tell us if we've got any missing values, and we don't seem to. We've got 465. So 465 observations or participants in this particular case. It's quite a big data set. But what we want is to run this chi-square test on our categories, categorical data, religion and race, although they've got these numerical code, dummy codes. When you import data, pandas will do its best to interpret what it thinks the correct data type is, essentially. And in this case, it's telling us it thinks it's integers, but it's not. So we're going to have to convert religion and race to categorical variables. So I'm going to do that first. So I'm going to convert religion to a categorical variable and create labels for the individual values. So at the moment, it's shown in the data frame as 1, 2, 3, 4. They're the 4 different levels, 4 different religions that are recorded, and these relate to other, Catholic, Protestant, Jewish. So I'm going to create an object that's just a list of those 4 integers, 1, 2, 3, 4, and then I'm going to create another object called B. So the first object I'll call it A, the second object I'll call it B, and that's going to be the labels. So other, Catholic, Protestant, Jewish. So 1 is other, 2 is Catholic, 3 is Protestant, 4 is Jewish in that data set. That's how they were dummy coded. So I'm basically, what I'm going to do is I'm going to create a new variable called religion, and I've put an underscore at the end of it. So it'll leave our original religion variable column as it is, and it will append a new column, a new variable called religion underscore. I could have called it religion category, something like that, or labeled. And I'm going to use the dot map function. I'm going to pass a dictionary to it and use this zip function. And what I'm doing is I'm then specifying object A and object V. So what that's going to do is zip together, if you think zip up objects A and B. So it's going to match quite cleverly. It's going to match the labels with the correct values in the data frame. If I run this, so I haven't run that cell yet, have I? Let me run that cell. And if we call the head, you can see now we've got this extra religion underscore, and so 3 was Protestant, you can see 3 Protestant, 2 is Catholic, 1 other, 4 Jewish, so looks like that's worked correctly just on a quick visual inspection. So that's religion. We've got to do the same thing with race. So we've got we need to use those integer values and add the labels to them and create like a categorical, convert that from an integer to a categorical object, so to speak. This time I'm gonna do it in place. I'm not gonna create if you've watched any of my previous videos, you'll know that I often, when I do something like this, like add labels or map a categorical values for a categorical variable to dummy codes or add labels to them, I kind of often like to do what I just did with religion, which is leave this one alone, just create a new one that is kind of so it makes the size of your data frame larger, but doesn't harm anything. But this time I will do the opposite, and I will change this race variable in place and just change the numeric values to the actual label. So to do that, I'm going to create an object called C for categories, and those are 1 and 2, and L for labels, and those are white and non-white. And I'm going to use the same procedure as I did above, but this time I'm specifying the new object health race is the same. I've not given it a new name, so it's not going to append it. It's just going to change this variable in place. And I'm going to use the dot map, pass it a dictionary, use the zip function. I'm going to tell it to zip up objects C and L. So it's going to zip together white with 1, non-white with 2. So let's run that. Call the head, and you can see there it hasn't appended a new variable. It's just kind of converted these. So well, those first ones were all 1, weren't they? So they're all, yeah. So that looks correct. They're all white essentially. Okay, so if we look at the data types, we can now see that race and religion are not shown as integers anymore. They're shown as objects, which is what we wanted. Okay, so let's now extract the 2 variables that we want, the 2 categorical variables, and create a cross tab. So we're going to call it health underscore tab for health cross tabulation, and we're going to use the pandas pd.crosstab method. And the 2 variables I'm going to pass to that are health and then square brackets religion underscore. So that was our religion categorical labeled value variable, and health race. So let me run that. And there we see we've got so the first argument was the kind of row index, the second argument was the column index. So what you can see there is we've got this cross tab of the frequency counts, and we can see we've got Catholic, Jewish, or the Protestant, and then we've got as a column non-white and white. There's obviously more participants that were white than non-white, but then we can see the counts of 25 non-white people were Catholic and 94 white people were Catholic. So we can run the chi-square test on the above contingency table. And to do that, we're going to use, I demonstrated in the previous video when we did this test of independence, we are going to use the stats.chi__contingency, and what we pass to it is just the observed data. And in this case, the observed data is this, which is saved as the object health_tab for health table. And what I've done in terms of the things it's going to return, there are a number of it gives the output can give us the chi-square value, the p-value, degrees of freedom, and it will return this kind of array of expected counts. So these are our observed counts. It'll tell us what the expected counts should be. So we'll be able to see if there's a significant association, and we'll be able to look at this table and look at the array it returns of expected counts to see kind of where they differ. Okay, so let me run this particular test. And what we see is so I've not asked for a critical value in this case because we're getting a p-value, so we'll know we've exceeded a critical value. We could calculate that manually. There is no sort of easy way to do that other than to know how the critical value is calculated and use like the symbolic mathematical manipulations available in Python to do that, which is what I've done in previous videos. But what we're seeing here is we've got a chi-square test statistic of 32.45. If we round that to 2 decimal places, we've got a p-value of 4.21 times 10 to the -0.07. So what we're seeing here is if we take this decimal point and we move it 7 places kind of to the left, that will give us the actual value. So we'd have to move it. This is telling us if this was a positive, say e to the 7 or something like that, then we'd be moving the decimal place this way and we'd be getting a very big number. Because it's kind of scientific notation, e to the -7, we're kind of moving it in the other direction again, a very, very small number. This here gives us an indication this is a very small number, and it's what Python has done is abbreviated it rather than print the exact value because it's much lower. It's much lower than less than 0.001. Okay, so we could specify this as p is less than 0.001 to save us doing it exactly precisely to 7 decimal places. So we've got what we're finding here is we've got a significant chi-square statistic. The 3 here is our degrees of freedom. Okay, so remember to work that out when you have a contingency table like this, it's the degree of freedom is the number of rows minus 1 times the number of columns minus 1. So in this case we've got 4 rows, so -1 that's 3, and we've got 2 columns, so -1 that's 1. So 3 times 1 is 3. And then we've got the array here, which is the expected count. So let's have a look in comparison. So what's based on the way the expected values are calculated, which is, I kind of mentioned it in a previous video, you work out, you basically take the row total and multiply it by the column total, then you divide by what we could call the grand total, or the total number of observations. In this case, that would be 400 and something. What was it when we looked up here? 465. Okay. Okay, so we can see here that what was expected was for non-white Catholics there would be 10, roughly about 10, and white Catholics there would be roughly about 109. But we're seeing we've got 25 non-white Catholics and 94 white Catholics. Let's look at another one because these are when we do the post hoc test, we'll see this is where the significance is. If we look at the Protestant, we've got 6 non-white Protestant. What was expected, if we look at this bottom row here, was 15 non-white Protestants. So that's the observed is much lower than was expected. And we've got 169 white Protestants, and what was expected was about 160, so that is higher. Okay, so Given that we're seeing these differences, how do we know where the significant differences lie? And there are a number of, I've seen this done a number of different ways. So if we follow, so we've got a significant chi-square test. We know that these two categorical variables are not independent. There's some sort of association between race and religion, essentially. Yeah. Based on this data, but I think it came from LA in the 70s or something like that. So this significant chi-square tells us the variables are not independent, they're significantly associated, but how do we interpret where that significant association lies? So we can eyeball contingency tables like I just did, but that can be misleading, and what might look like a large difference between observed and expected counts can be hard to interpret as to whether those differences are statistically significant. And I've seen this done in a number of different ways over the years, such as people working out column percentages and comparing them. But there's no eyeballing the data and looking at proportions, looking at percentages, looking at the raw values expected against observed. It's not going to be. It's going to be relative, it's going to be subjective. You're not going to be able to tell exactly where what might look like a big difference might not be statistically significant. Okay, there are no existing packages to conduct this type of post hoc test that I'm going to do, but two that are kind of two that I prefer to use these days are standardized residuals and adjusted standardized residuals. So adjusted is probably better because adjusted residuals are kind of the raw residuals, so that's the difference between the observed and expected counts, and then we divide by some sort of estimate of the standard error, and that doing that accounts for the variation that we might see due to kind of the sample size. So different size samples. A larger sample, you're more likely to find a significant result with a small difference between observed and expected. But if we use adjusted residuals, we can control for that to some extent, so we're not making type 1 errors. So what adjusted residuals are? They're effectively z-scores. So if an adjusted residual is greater than 1.96 or it's less than 1.96 kind of standard deviations from a mean of 0, then it's going to be significant at the 0.05 level. And what it would do, so if it was greater than 0.06, it would indicate that there were more counts in that cell than expected if the null hypothesis was true and there was no association. If it was less than with 1.96, it tells us that it was significant at the 0.05 level, that there were fewer counts than expected. And we're seeing with some of these here, we're seeing kind of more than expected and fewer than expected, yeah, in different cases. So what I will do is manually calculate the adjusted residuals, and there are a few steps I'm going to have to follow to do this, to code it. So first of all, we need the raw totals and row totals and common totals for our contingency table. We also need the number of rows and numbers of columns. That's kind of straightforward. We know how many rows we've got. We've got 4 columns. We've got 2. That type of thing. But what we're going to do is I'm going to create some new objects. Number of column totals and number of columns. Column totals is just we're going to take our health table, which is our observed, this one, and we're just going to use this sum method. For the number of columns, we know it's 2, but we can kind of work it out using, rather than just specifying n columns equals 2, we can do length of col totals, which is this, and then we can print those out. So if I run that, what you see is we get n cols is 2, and then column totals for non-white we've got a total of 40, and white we've got a total of 422 observations. Okay, so that's our that's to obtain the column total stuff. that we might need to work out our adjusted residuals. We do the same thing for row totals and the counts. So exactly the same. I'm doing row totals. I'm using that health underscore tab dot sum. This time I'm specifying axis equals 1. Okay, so it's going to total to work out the row totals. It means summing everything in the columns, so to speak. So if we look at this table here, if it had the row totals, maybe we've got one with row column totals. No. If we had the row totals, it's a row totals or something like sorry, row totals, but it'd be here, and it'd show you the total for this row here. So it'd be a column. If you had the column totals, it'd be here, and it'd show the total of this column here, so to speak. Yeah. Right. So let's run this. We'll get a number of rows, number of totals. So we see we've got 4 rows, 119 Catholic, 92 Jewish, 76 other, 175 Protestant is our totals for each of those. Okay, for each row, number of participants that fall. If we ignore race, these are the totals for each religion. And here, if we ignore religion, these are the total number of non-white and white participants. Okay. It's also useful to have the grand total. So we're going to obtain that, we're just going to take the row totals and sum over the row totals, which remember these 4 values here. If we print that out, gives us a total of 462. So maybe we've got some missing values. Okay. So with that, we've got row totals, column totals, we've got the lengths of each, we've got a grand total. We now have everything we need to fill out the adjusted residuals formula. Okay, so I'm not going to say too much about how the adjusted residual formula, but what I'm going to do to calculate it is use a for loop. I'm going to do nested for loops. In fact, I'm going to use a for loop here. This is for I in range n rows. So what that's going to do is basically iterate through the number of rows we've got. Yep, 4. And the values that feature in there. And for j in range n columns, that's going to iterate through the columns. And then it's going to, we're going to create this object called adjRes, so adjusted residual. And that's going to be our health tab dot integer location, and then pairs of rows and columns minus what we're doing here is expected value of I and j divided by expected value of I and j, so row and column pairs, and then we're going to multiply it by 1 minus the row totals for our rows divided by n, and we'll multiply by 1 minus the column totals, which is our all j values relating to the column totals, divided by n, and we're going to raise this to the half power. Okay, and that's going to give us our adjusted residual. So if I print that out, what that's done is for each, it's given us adjusted residuals for, if we look here, we've got 8 altogether. We've got 8 values, and it's going to give us 8. This will have given us 8 as well. So for each of our cells, it's given us it's telling us how much, in terms of z-score, standard deviations, how much above a mean of 0 it lies, how much below. Okay, so that's quite useful, but it'd be useful to know what cells these relate to, and we can achieve that by basically creating a nice data frame that kind of. So we just got a list of 8 here. We maybe we could work out maybe they're in row 1, column 1, row 1, column 2. But rather than worry about that, we can achieve this by creating a data frame as follows. So I'm going to create a data frame called health underscore results. I'm going to use the pd.dataframe method. I'm going to pass in as columns religion, race, and a third new category, which is going to take these values, adjusted adj.res, adjusted residual. And then I'm going to use these nested for loops. I'm going to loop through the rows, loop through the columns, pair them up, run our adjusted residual again, our values, and then this time I'm going to return this health res data frame object, and I'm going to append, if I scroll across, it might be easier to see there, basically I'm going to append the religion and race and adjusted residual to each one. Let me run that and hopefully be able to see what that has done. Okay, so it doesn't like what I've done because it's kicked up a load of warnings saying certain aspects of concat and append are deprecated in future versions, but it has worked. It has worked. But so what you can see now is where above we had this list of 8 adjusted residuals, and we was like, okay, so maybe that's non-white and Catholic, maybe that's, you know, that type of thing. We can see which ones they relate to here in this table. So we can see, yeah, 5.56 adjusted residual of non-white and Catholic. So those are, as I've said, those adjusted residuals are z-scores, and we can interpret the significant deviations from a mean of 0 for a standard normal distribution. So those that are greater than 1.96 are going to tell us that there's significantly more counts than expected in that cell. Those that are less than 1.96, so negative 1.96, there's going to tell us that fewer counts than expected in those cells. We can see by eyeballing what some of these are, but we can convert them to the corresponding probabilities for the standard normal distribution using the norm dot cumulative distribution function from scipy. So I'm going to import basically the normal distribution from scipy in order to do this, and then we'll do some more manipulating to get this to get these adjusted residuals. So what I'm doing is creating a new object called AR_6, so adjusted residual significance, and I'm going to use the np.absolute, so it's going to take the absolute value of each of our adjusted residuals. So at the moment, some of them are positive, some of them are negative, you can see there. So if I run this, they'll all be positive values. They're just the absolute value, the absolute deviation from 0 of each of those. You can see they're now all, and they're saved as objects at the moment for some reason. Saved them as data type object, but we want them to be floating point numbers because we want to do some sort of numerical manipulation on them. So what I'm going to have to do here is convert them basically to numeric values to floating point numbers. So what I'm going to do is I'm going to save these as a separate object called adjusted residuals underscore absolute value of, and I'm using the pd.to underscore numeric method. I'm going to pass this object, our adjusted residual significance object, and I'm going to downcast it as a float object. So let me run that and call it, and you can see now here they're no longer objects, they're saved as floats. Okay, so again, wrangling data in the middle of the analysis here, it's kind of, sometimes it's an essential thing to do. So the above object we just created is now has float values that we can use in the formula to find their respective p-values. So to get their p-values, what we're going to do is I'm going to create a new object and I append it to this health results data frame and call it significance. And to calculate the p-value associated with each of those adjusted residual absolute values, I'm going to take 2 times, then in parentheses I'm going to do 1 minus normal distribution, norm.cdf, cumulative distribution function, and I'm going to pass the adjusted residual absolute values that we created above. If I run that, so what I've done there is I've basically said for whatever these absolute values are for each one of them, use the cumulative distribution function, tell us what's the probability of getting this value or more extreme, and that's what we're seeing here. We're getting a significance value. Remember, we've got these e to the -3, e to the -1, e to the -8, so we'd have to move our decimal place to the left significant number of places, so these are very small values indeed. Okay, but the problem we've got here is we've not used a robust test as such. We've conducted 8 comparisons here, so we needed some sort of correction. We needed some sort of correction, adjustment of the p-value based on the fact that we've done 8 tests. Otherwise, we're increasing our probability of committing a type 1 error. And you will see that some of these all look like they're significant at the moment, but when we do a more robust, when we kind of adjust them using some sort of method, such as Bonferroni, we'll see that not all of them are. And we definitely need some sort of adjustment there. So let me just run this. You can see we've got significances afloat. These other values are saved as objects. So what I'm gonna do here is a kind of type of Bonferroni correction, which is I'm gonna take the existing p-values and I'm gonna multiply each p-value by the number of tests we've done. So usually when you do a Bonferroni correction, you learn about it. You kind of take whatever your p-value is and you divide it by how many tests you've done, that type of thing. In this case, what I'm going to do is for each one, I'm going to use I'm going to create this new, I'm going to create a new variable and append it called adjusted significance level. So we differentiate from the significance level that's not been adjusted. I'm going to take the health results data frame dot shape, and I'm saying here I'm passing 0 to tell it to use the index, use the rows as the index, and multiply by the health results significance. If I run that, what we will see is we've now got another column with kind of significance values here, but with like corrected significance values here. So adjusted significance values, so they're more robust. Okay, and we can see that now not all of them are significant. Yeah, in fact there's only 4 of them now I believe are. Okay, so last thing I'll do just to make that easier to see, because it's written in scientific notation and it's quite safe to a quite precise level of decimal places. So what I'll do is I'll add another new significant. I'll add another variable to the end of here. Call it adjusted significance new, and I'm just going to round to each of these to 2 decimal places. So what I'm doing is saying round. Take this variable and round it to 2 decimal places. Let me run that. Okay, so what you can see here now is, in terms of our threshold significance level, so p is 0.05, you can see that we have a significant result here for Catholic non-white, Catholic white, and for Protestant non-white and Protestant white here, right? And we've got our adjusted residuals. This one's positive. So what this is telling us is, so non-white Catholics, this is a positive adjusted residual. So it's significantly higher than the mean. Okay. So we've got we've got significantly more non-white Catholics than expected. This is a negative residual, so we've got significantly fewer white Catholics than expected. I guess that makes sense if you kind of, if more were non-white, then fewer have to be white than was expected if you're taking the total number of Catholics. And then for Protestants, we're seeing non-white, we've got a -3, so we're seeing here that we've got significantly fewer non-whites were Protestant than expected, and significantly fewer more whites were Protestant than expected. Looking at the observed counts, and kind of if we go back and look at that table of kind of the data values, let me scroll back up. There we go. So what we've seen is we've got a significant association between race and religion, and significantly more non-whites were Catholic than was expected, and significantly fewer whites were Catholic. And then at the same time, we had significantly fewer non-white Protestants than expected, and significantly more white Protestants than expected. But we wouldn't have been able to tell that just from looking at, just from eyeballing the data here. So, if we haven't got a significant association when it comes to race and and the Jewish religion. But if we had just eyeballed this, we'd have seen that we observed 3 non-white Jewish participants, but expected about 8. So we might have just by eyeballing that erroneously concluded that there were fewer non-white Jewish people than expected, and more white Jewish people than expected. But that wasn't a significant result. It was the Catholic and the Protestant cell counts that were driving the significant association. Okay, so that is far too much information, I think, about chi-square. It's not a test. It's not something that I use very often. But the point I think that's worth thinking about with this is if you do a test of independence, you're looking to see if there's an association between two categorical variables. It uses counts, not the actual values of the data. And if you find you've got a significant chi-square test statistic, then a useful way to assess where the significant differences lie is to use adjusted residuals, as I've done in this case. I think that you can use standardized residuals that will just give you Z scores in a similar way to adjusted residuals, but adjusted residuals take account of the size of your sample, so you're not likely to erroneously think you've got a significant difference just because you've got a large sample. Okay, I hope that was useful. I must stop now.